Module Technical Course Additive Manufacturing for Industry 4.0. Lecture 3, Additive Manufacturing Design Guidelines. During this lecture, we will discuss the main stage of additive manufacturing cycle and recommendations for the design of parts. Examples of real designed and printed parts will be shown. The production cycle of additive manufacturing begins with the processing of a 3D digital model, which is divided into layers and oriented in the most appropriate way for printing. Slicing is a process of translating a 3D model into control code. If necessary, support structures are generated for printing overhanging elements. The issue of choosing the appropriate slicing software with settings to ensure the quality of the printing process, taking into account time and material constraints, is relevant. Slicing software works with different file formats, but the stereolithography file format is one of the most popular. It is supported by most computer-aided design packages, and it is widely used in most rapid prototyping additive manufacturing technologies. STL files only describe the surface geometry of a 3D object without any representation of color, texture, or other common 3D model attributes. Information about an object is stored as a list of triangular faces that describe its surface and their normals. STL file can be text or binary. A 3D printable model must be correctly geometrically designed in order to successfully print the finished product. Model limitations that can affect the quality of the result include various characteristics: wall thickness, design feature, geometry, etc. To start 3D printing of a product, it is necessary to add volume or thickness to the surfaces. Another requirement is the absence of tangent surfaces and faces in the model. Therefore, if the tangent parts make up a single model for printing, it is better to combine them. Otherwise, the mating parts must be separated with the minimum setback provided for each specific material. The last requirement is especially typical for all printed mechanisms and moving parts of models. In the manufacture of prefabricated parts, it is necessary to provide a gap between the mating surfaces in order to minimize the machining of finished products before assembly. The gap is selected individually for each material, which will allow the node not to stick together during the manufacturing process. It is also important to determine before printing how to remove unused material, powder or washable support from the gap between the moving parts. When designing parts for additive manufacturing, attention must be paid to the minimum dimensions of holes and other elements, for example, text and small decorations. In this regard, recommendations are individual for each material and additive manufacturing equipment. It should also be taken into account that after cooling, the material can shrink, and at the same time, the geometry of the object changes. There is also a software side of the problem. Not every slicer correctly handles internal dimensions, so it is better to increase the diameter of the holes. When modeling, it is also necessary to take into account the maximum possible dimensions of the printing space. If the model is larger than the dimensions, then it must be cut in order to print in parts. Each overhanging element requires a supporting structure. The fewer overhangs, the fewer supports you need, the less material and printing time you need to spend on them, and the cheaper it will be to print. It is allowed to print without supported wall, which have an inclination angle of not more than 70 degrees. Sometimes it makes sense to create artificial support in the model itself. One of the main requirements for the design is the need to comply with the minimum wall thickness of the model and its elements. First of all, the minimum thickness depends on the material used and the printing method. The use of models with minimum wall thickness is allowed, but not recommended. The walls must be equal to or thicker than the nozzle diameter. That is, the wall thickness should be a multiple of the nozzle diameter. Thus, the thickness of the walls and structural elements of the model must be sufficient to withstand certain loads in the framework of fulfilling the functional requirements assigned to the model. The geometric ratio of the parts of the model must correspond to the functional strengths and aesthetic purpose of the product. The use of large, thin, unsupported surfaces is not recommended due to the possible curvature of the surfaces during the manufacture of the model. When talking about the accuracy of the printer, they mean the positioning accuracy of the print head, which depends on the control scheme and the quality of the mechanical components. The higher the accuracy, the better the side surface of the model will be. The figure shows schematically what happens to the side wall if the positioning accuracy is insufficient. The resolution of printing is determined by the diameter of the nozzle. To obtain sufficient strength of the model and reliable fusion of plastic, printer manufacturers recommend making the outline of the object in two passes. Each layer consists of a perimeter and of fill. The model may have a different percentage of filling, and there may not be a fill for hollow model. In the figure, the outer contour of the object is marked in red, the inner contour is green, and the inner filling is yellow. Options for the structure of the internal filling can be of various types, as shown on this slide. The substrate is the basis of the model made in the form of a grid. Due to their high porosity, such structures cool quickly and evenly, and then serve as a reliable basis for the printed part. The larger and thicker the substrate, the stronger and more reliable it is. However, you will have to find the perfect balance between functionality and material consumption. The slide shows various options of the substrates: a skirt, a brim, a raft. How to place the model on the desktop depends on its strengths. The load must be distributed across the print layer and not along. Otherwise, the layers may disperse. To make it clear, let's look at two L-shaped models. The lines show the layers of print. The strength of the printed part depends on how force is applied to the layers. In this case, the weak point is shown for a part that can be broken with little force. The figures on the right show different placement of the part to be printed. In the case of the second placement option, it is obvious that additional support structures for printing process will be required, which is undesirable. The main stages of information technology for creating a physical prototype of a robotic arm are shown on the slide. These are pre-design, design, and manufacturing. The first step is the creation of structural diagram of a design product based on the principles of hierarchy and decomposition. Prototype contains separate parts: finger, palm, base of the thumb, and an assembly subunit: the palm plus base of the thumb. The pre-design stage also includes an analysis of the design features of the product components and identification of properties. PTC Creo parametric software can be recommended for developing a virtual prototype of a robotic arm, as it is one of the best computer-aided design environments in the world. The system has powerful functionality and provides an intelligent design and parametric modeling environment. After the creating files with 3D models of all 5 fingers and palm in Creo parametric, it is possible to develop the 3D model of the entire assembly. It is convenient to send all the fingers for 3D printing at once rather than each finger separately, and also to evaluate how the artificial hand will look in the final. Tabular parameterization is widely used in the computer-aided design to quickly build models of similar parts, fingers in our case, based on one parametric description. For its implementation, the CREO environment, a table with dimensions and simplified equations for calculating model parameters must be implemented. After developing 3D models in CREO parametric, STL files can be generated as input data for the simplified 3D software. This software performs slicing of the 3D model for the 3D printing process, as well as sets the print options. The mechanical parts of the designed physical prototype, fingers, palm, base, or the thumb, can be made using fused deposition modeling additive technology. The Leapfrog Creator printer uses non-toxic ABS plastic, which is resistant to adverse operation conditions and has a low cost. A general view of the developed, printed, and assembled prototype of the robotic arm is presented on the slide. The hardware of the prototype includes an Arduino board, the set of servos, mechanical and electrical connections. Functional testing of the prototype was carried out in several scenarios, blending individual fingers or several of them. The results confirmed the performance of prototype as well as implementation of the main functions. Thus, the technology of virtual prototyping using parametric modeling allows to quickly design a product and manufacture it in an additive way. On this slide, you can see the list of mistakes to avoid when creating a 3D model for additive manufacturing. Do not take into account the features of the material, ignore 3D printing technology, do not consider wall thickness, do not take into account the resolution of the STL file before printing, and ignore the recommendations for using the software. On the slide, you can see recommended sources of information. Thank you for your attention.